Completely simplifying that, 2 plus 6 plus 2 is 2 plus 6 is 8 plus 2 is 10. 3 plus 2 is 5. 5 minus 1 is 4. 6 plus 3 plus 6 is 15. 9 plus 1 is 10. 10 minus 3 is 7. And as we predicted, we ended up with a 2 by 2 matrix. Now moving on to more examples. Example 3 here. The first thing you always need to check is the size of the two matrices that you are looking at. So what is the size of this first matrix? How many rows does it have? 1, 2, 3. So it's a 3-row by how many columns? 1, 2. Oops. And then the other matrix has how many rows? 1, 2. And how many columns? Looks like 3 to me. So can you multiply these two together? What are you supposed to check? You check if this number and this number are the same, which they are, and you will end up with a 3-row by 3-column matrix in the end. So 3 rows and 3 columns. I'm creating 3 rows first. Hope this is big enough. And then 3 columns. Okay, so now, same idea. This is I don't know what's happening. Row 1, column 1. Row 1, column 2. Row 1, column 3. Row 2, column 1. Row 2, column 2. Row 2, column 3. Row 3, column 1. Row 3, column 2. Row 3, column 3. Okay, so row 1 with column 1. That means row 1 here, 2 and 3, will get multiplied by 1 and 3. The 2 is the first thing in that row. It will get multiplied by the 1, the first thing in that column. So 2 times 1 plus this 3 gets multiplied by what? This 3. Then we'll move on to row 1 with column 2. So the 2 and the 3. The 2 and the 3 is going to get used again. This is my theory of it. The 2 and the 3 gets distributed to here. Then it gets distributed to here. And then it gets distributed to there. We're currently on the 2 and the 1. So right now, the 2 will get multiplied by the 2, and the 3 will get multiplied by the 1. So that goes here. It's 2 times 2. I guess I should match up my colors again. 2 times 2 plus 3 times 1. And then again, the 2 and the 3 will get brought through to the 1 and the 3. So the black 2 will get multiplied by the black 1. And then the blue 3 by the blue 3. We have now completely finished threading row 1 through each of the 3 columns that were available. So now we're done with row 1. The same logic applies, but this time we are going to take row 2 to column 1, to column 2, and to column 3, one at a time. So row 2, I think I might circle the whole row here, because this is the one we're focusing on, or at least point to it, I guess. This 3 and this 1. This 1 with this 3. So 3 times 1 plus 1 times 3. Now we go to the next one. The same row, but then this 2 and this 1. So we are on 3 times 2 plus 1 times 1. Last row and column. This 1 and the 3, this 1 and that 3. Oops, I have no idea what I just did. So I'm taking the 3 times the 1 plus the blue 1 with the blue 3. Almost done. I'm going to erase all of that. So you can kind of follow what's happening, because now we're done with row 2, and we have to redo all of that with row 3. So we'll be here on row 3, and I'm going to take row 3 to each of the columns in the other matrix. This 2, this should be black, hold on, for consistency's sake, oops. This 2 times this 1, this -1 times this 3, then the next column, the same 2, but now it's going to get multiplied by this 2, and this -1 times that 1. Last column, this 1, this 3. So it's 2 times 1 plus -1 times 3. Simplifying all of that, I may try to squeeze this in here. I don't think I can. 2 plus 9, 4 plus 3, 2 plus 9, 3 plus 3, 6 plus 1, 3 plus 3, 2 minus 3, 4 minus 1, 2 minus 3. And simplifying that further, it's 11, 7, 11, 9, 7, 9, -1, 3, -1. So now, I was hoping that we would notice something. You just look at that final answer. I'm going to zoom in again and erase all of this mess I made, because we need to see these matrices for what we're about to discuss. I'm going to go back to page 5 and also show you this matrix. Aren't these the same two matrices, just in different orders? In this one, the 1, 2, 1, 3, 1, 3 is second, and here it's first. Oops, I'm trying to point, not erase. And 2, 3, 3, 1, 2, negative 1 is the same matrix here. My question to you is, did we get the same answer? When we had 1, 2, 1, 3, 1, 3 first, we end up with a 2 by 2 matrix. When we had 2, 3, 3, 1, 2, negative 1 first, we ended up with a 3 by 3 matrix. Completely different answers. Which brings us to this comment right here. Note, in general, matrix A times matrix B will not give the same answer as if you reverse the order. So now we'll just try a few more examples. So here we're going to find A times B. So matrix A, well, before I do anything, let's find out the sizes. The size of matrix A is 1, 2, 3 rows, and matrix B is 1, 2, 3 columns, and matrix B is 1, 2, 3 rows by only 2 columns, so again, what are you checking that is the same? This number and this number, they are. So we end up in the end with a 3 by 2. Wow, that took up all the space I had for this problem. So I guess I'll be doing it over here on the right. 1, 2, negative 5, 3, negative 4, 7, 0, 9, negative 2. Oops, I don't know how I do that by accident. And B is 1, 7, negative 5, 3, 1, 4. And we're going to end up with a 3 by 2 matrix. So again, I like to do my 3 rows. And 2 columns. So hopefully it's making sense that this row, row 1, is getting fed through column 1. So row 1 to column 1 will be lined up like that. So it's 1 times 1. I keep trying to write, but it keeps being my hand on the thing instead. 1 times 1 plus 2 times negative 5. We don't have enough space. Plus negative 5 times 1. Now row 1 with column 2. Oh gosh, this is not working out very well because it's not printed.